Okay, so now we are going to talk about, so far what we've done is we've discretized the equation, we have our system of equations, now it's time to solve them, okay? And obviously a computer cannot solve the ODE or PDE directly, so we have converted them to algebraic equations using the finite difference method in this case, but we could have used other methods, okay? Bottom line is, at the end of the day, we have a system of simultaneous equations, okay? Notice that these equations are simultaneous, or what are called implicit, because you can't solve them one at a time, okay? To solve phi2, for example, you need phi1 and phi3. To solve phi3, you need phi4 and phi2, and so on, okay? They're all coupled, simultaneous. Okay. Now, one of the things we also do, and I'll talk about this later on, is we linearize the system of ODEs or PDEs if it's nonlinear, and I'll talk about that later on, not right now. But after all that is done, we get a system of linear algebraic equations. Okay? And they're implicit or coupled. They cannot be solved one at a time. And in fact, this is one of the most intense areas of research in numerical mathematics. Okay, people spend whole lives trying to develop robust, efficient ways of solving set of simultaneous equations, and we'll talk about that, why that is so challenging. Okay. So let's talk about a class of solvers now that are called direct solvers, and you will understand in a moment why they're called direct solvers. Okay. So if we take a system of, let's say, 3 by 3 equations, so a11 x1 plus a12 x2, a13 x3 equal to b1, and so on. Okay, just 3 equations. The reason I'm using a 3 by 3 system is because the mathematical or the algebraic operations that we do to solve this is fairly easy to see and understand. They're transparent, okay? If we have an n by n system, it's not as straightforward. So the way we have been solving these equations, and this is right from our early childhood, okay, is we substitute for one of the variables into the other variables, and then we eliminate that variable, and then we do that for the next equation and the next equation, and continue doing it until we find that we have one equation where there are no other variables and we can solve for it. Okay, and then we go backwards and substitute that into the other equations. So this is the procedure we have always used, and so the step is really, we take the first equation, this guy, we express x1 in terms of x2 and x3. We plug that into the second and third equation. Okay, so when we do that, this is what we get for the second and third equation. So notice that now I've gotten rid of x1 completely in favor of x2 and x3. So these equations only have x2 and x3, no x1 anymore. Okay, and if you simplify and rearrange, this is what you get. Okay, notice that the right hand side has also changed. They're not B2 and B3 anymore. They're B2, some modified B2 and some modified B3. Okay, if I write all this in matrix form, this is what I get. My first equation I've kept intact. Second equation, third equation, they have changed. Okay. Notice that the first column in the second and third equations are missing. Essentially, we have zeros here. Okay? Everybody with me? All right. So what has really happened is the aij, if you really look closely, okay, got replaced by aij minus ai1 divided by a11 times a1j. Okay, where j is any number going from 1 to n. Okay, that's really what has happened. If you look at this expression, that's the general formula that is being applied for all of these guys. Okay, and similarly, the B2, BI got modified with that kind of an expression. Okay. Now you can continue this process. We did it only once. Now you can take the x2 from the second equation, write it in terms of x3, and then plug it here in the third equation and get rid of the x2 in the third equation. Okay? Just like we took x1, plugged it into 2 and 3, got rid of this guy, you can take x2 in terms of x3, plug it in here, get rid of this. So you are going to end up finally with another 0 right here when you do that. Okay? So ultimately, your matrix is going to look like that after you've done one more elimination step. You're going to have a so-called upper triangular matrix with zeros in the bottom half, non-zeros in the top half. Okay, those A22, A23 stars I've written because they're modified coefficients. They're not the original ones that we started off with. Okay, the same goes for the right-hand side. So this process that we just discussed, this is called forward elimination. Okay, where we are eliminating variables, the unknowns one after another successively. Any questions so far? Now you all know this. I mean, this is not anything fancy. This is you've learned this very early on in your math education already. We're just generalizing it to, and the reason I'm discussing this is pretty soon we will come to some conclusions that are very important. Okay. So the next step is we solve backwards. Okay, we have done the forward elimination. Now we are going to do what's called a backward substitution. So what we do is we solve for x3 first, and we get b33 divided by a33, and then we plug that into the other equation, the second equation, and we get our x2, etc. Okay, so that's the backward substitution. So, and the backward substitution formula in general you can write as that. Okay. And the combined process of forward elimination and backward substitution is known as Gaussian elimination, in short. Okay, it's actually called Gauss-Jordan elimination, but in short we call it Gaussian elimination. It has the whole process has no approximations. Okay, we are obtaining the exact solution to the equations. When you do this on a computer instead of a paper, okay, the only caveat or only drawback there is the precision of the computer. Okay, you could get some round-off errors. In fact, Gaussian elimination has many derivatives. If you try to use Gaussian elimination for matrices that are very stiff, sometimes you get totally wrong solutions on a computer. Okay, now what we call stiff is when if you take, let's say, one row of a matrix and one element is, let's say, 10 to the power 10 orders larger than one of the other elements. That's called a stiff matrix. Okay, where the magnitude of the different elements are way apart. All right. When you use Gaussian elimination for such a matrix, sometimes you get into big problems. Okay, that's well known in numerical mathematics. But we're not going to get into that. Bottom line is, for most cases, Gaussian elimination gives you an exact answer on a computer. Okay, especially if you're using double precision calculations. All right. So that is why this kind of a solver is called a direct solver. There are no approximations. It gives you the analytical solution to the problem. Okay, so here's this is just for your benefit. Here's a pseudocode for Gaussian elimination. So our inputs are the number of equations, the coefficient matrix, the right-hand side, okay, and the output is x, which is the solution vector. Okay. So basically, it has two steps. This part here is the forward elimination part. Okay. Now you notice here that there are three nested loops. There is this top index k going from 1 to n minus 1. Okay. There is this second index which is going from k plus 1 to n, And then there is this third index going from k plus 1 to n. Okay. Now, of course, k is going from 1 to n minus 1. So by the time you get to the second loop, you may not be going from 1 to n. You may be going from 3 to n or 4 to n. Okay. So this is not really, if you think about, so at the innermost loop, you have this multiplication right here. That's one multiplication. Okay. So in the inner loop, if you think about it, this is not being done exactly n cubed times, because some of the loops are not running 1 through n. They're actually running part of the space from 1 through n. If you really try to count the number of long operations or multiplications in that innermost loop right here, you will find that you will get a geometric series. Okay, and then you sum the geometric series, you will get a certain answer. In addition to that, there are multiplications here. So that is outside of the innermost loop. So that's really n square operations, again, or close to n square, because again, the index is not going from 1 to n. And then there is another multiplication here, okay, which is also very similar to n square. So you get, if you count the number of long operations, why are we interested in long operations? Because that's what takes the longest to compute on a computer. Okay. Typically, division takes a little bit more time than multiplication, but for the purposes of our analysis, we'll say it's the same. Okay, so multiplication and division will count as the same. Okay, so if you count the number of long operations in this forward elimination step, you can show, after you sum up all those geometric series, you can show that it's approximately n cubed over 3. That's the number of multiplications or divisions we are doing in the forward elimination step. Okay, any questions? Yeah.
So adding and subtracting take
Negligible time, yeah. And here's the backward substitution. Here you have only two nested loops, that guy and that guy. Okay, and there's only one multiplication here. So that's about n square operations. Okay, and then this guy you can pretty much neglect, that's n operations. So bottom line is the number of long operations scale as n square in this case. Okay, it may be some factor of n square, but as n square pretty much. All right, so forward elimination scales as n cubed, backward substitution scales as n squared. Okay. So in summary, the memory that you need to do Gaussian elimination is n square. Obviously, we have n equations, so we have an n by n matrix that we have to store. Okay. Now, it turns out that you might start with an equation which has only 5% non-zero, or start with a matrix which has only 5% non-zeros. Okay. By the time you do the forward elimination, you will find that 95% of them have become non-zeros. So many of the zeros will get converted to non-zeros. Okay, so you can't say that I'm going to store only 5% of the numbers and allocate memory for that, because that's what my coefficient matrix looks like, very sparse. Once you do Gaussian elimination, you have to allocate at least half that upper triangular matrix, memory-wise. Okay, but let's just say memory is n squared. The computational effort, which is the number of floating point operations we counted, scales as n cubed. Okay, and that is really, really bad news. Let me just, before we go there, now this is something we are going to be discussing a lot later on, but this is the reason why people don't use direct solvers for any numerical computation. You cannot use Gaussian elimination for any practical problem. Okay. Computational effort scaling as n cubed, that is really a nightmare. Why? Because that means, imagine you have a problem with 1,000 unknowns, you solve it in 1 hour. Okay, I'm just making up some numbers. All right, if you increase the problem size from 1,000 to 10,000, then that means that computation will take not 10 times more, 1,000 times more, 10,000 hours. 10,000 hours is a few weeks. Okay, it's not practically feasible. So as you go up in problem size, you are getting into a situation where Gaussian elimination is impossible to use. Okay, for any practical numerical computation like CFD, finite elements. Okay, well, finite elements does use direct solvers sometimes, but in most cases, that's just out of the picture. You can't use it. Okay, and that's why people use what are called iterative solvers as opposed to direct solvers, and that is what we are going to spend a majority of our time on in this class, how to do iterative solution of equations. Okay, the memory is also a big issue. Let me give you an example. So suppose I have a 100 by 100 two-dimensional problem, 100 by 100 mesh. This is pretty simplistic. I mean, this is trivial nowadays because, I mean, that's only 10,000 unknowns. Okay, nowadays people solve problems with billion unknowns. So 10,000 is trivial. Okay, but see what happens here. So your number of unknowns is 10,000. Okay, your n is 10,000. That means your memory n square is 10 to the power 8. Okay? In double precision, to store each real number, okay, so as I said, you have to allocate that amount of memory for real numbers. This is not integer storage. This is real number storage. Okay? For double precision, to store a real number, it typically takes 8 bytes. So you're talking about 8 times 10 to the power 8 bytes. Okay? Or you're talking 800 megabytes. This is not trivial. For a trivial problem, the memory requirement is not trivial. Okay? I mean, if you consider, okay, nowadays computers have RAMs of 3 GB, but 800 MB is pretty significant. I mean, if you go a little bit higher than 10,000, 10 to the power 5, that's it. You're out. Okay? And believe it or not, sometimes when I teach undergraduate classes and I ask students to solve these kinds of problems on a simple 2D heat transfer problem on a computer, and they use a 200 by 200 mesh, they come back and tell me my computer just hung up. I said, well, in MATLAB, you tried to use this / command, which essentially will do Gaussian elimination for you. And that's why it's hung up. Cannot afford the memory anymore. Okay? Any questions? So both memory and computational effort prevents us from using direct solvers. We would love to use them because, you know, they give us the exact answer, no iterations necessary, nothing. Okay, but it's not practically feasible. All right, now, what happened for the one-dimensional finite difference problem is that we got a special type of system, which is a banded system. Okay, and in this case, it was tridiagonal. Now it turns out that even if you go to multi-dimensions, 2D or 3D, you still get a banded system, and we will see that later on when we get to 2D problems. Okay, you will get 5 diagonals there instead of 3. Okay, if you go to 3D, you will get 7 diagonals and so forth. But the system of equations will still be banded as long as you use a structured mesh. Okay, and this is one of the advantages, as we mentioned, for structured mesh, that we get banded matrices. All right. So this is what we got for our problem. We got 3 diagonals, and these diagonals now, yeah. Good point. Thank you. Thank you for reminding me. Okay. So the structure that we are getting now is tridiagonal, and the 3 diagonals I have written as D, C, and A. Okay, D is the diagonal, C is the superdiagonal, A is the subdiagonal. All right. So those are three one-dimensional arrays or vectors that we have used here in this formulation here, and then the right-hand side we still use our B. Okay, and the solution vector, let's say, is X. Okay, now there are a couple of things that happen with these kinds of banded systems. First of all, if you look at just a simple, so if you now take your Gaussian elimination and keep it in your head that I'm not going from 1 to n, I'm just going from 1 to 2, because everything else is 0, right? So if you use that information and rewrite your algorithm, first of all, you see that the memory has gone down from n squared to just 3 times n. That's it. Okay? So remember, in the example we were saying our n is 10 to the power 4, n squared is 10 to the power 8, 800 megabytes. Now we have n is 10 to the power 4, 3n is 3 times 10 to the power 4. That's not even a few kilobytes. Okay? So tremendous reduction in memory because we are no longer storing the full matrix. We don't care about the zeros anymore. We're just storing these 3 diagonals. That's all. Okay? And if you look at the algorithm for, and this is the so-called Thomas algorithm, if you look at the algorithm for your solution, again, there's the forward elimination step. If you count the number of operations, you see there are no nested loops here anymore. Okay? Just 3 multiplications and divisions. So the number of long operations is 3n. If you look at the backward substitution, again, the number of operations is, there's 1 multiplication here, 1 division here, it's 2n. Okay? That's it. There's nothing else going on because this is diagonal. Okay, so storage-wise, we've cut it down from order n squared to order n. Most importantly, if we use a tridiagonal solver for a problem like this, the number of floating point operations going down from n cubed, order n cubed to order n. Okay? That's why we love tridiagonal solvers for simple problems. We don't want to use a full Gaussian elimination. It's a huge waste. Okay? So if we want to compare, one advantage is, as I said, we are storing only the 3 diagonals, so n squared to 3n, and then greatly simplified algorithm for the forward elimination as well as the backward substitution. Mainly the forward elimination is what we are concerned with because it takes the most amount of memory, the most amount of computational effort, and that has reduced by a factor of n squared. Okay.